Machine learning models often struggle with biased predictions, compromising their overall quality and fairness. Inference-Time Selective Debiasing offers a novel solution, particularly when retraining the model is not feasible. This approach draws inspiration from selective prediction, where low-quality predictions are discarded at inference time. Instead, the authors propose identifying potentially biased model predictions and applying a post-processing debiasing method, such as LEACE, to these predictions. Fairness in machine learning is crucial, as it represents the model's ability to classify instances without discrimination based on sensitive attributes like race, gender, and age. Various fairness definitions, including group fairness, are discussed, along with debiasing techniques proposed to achieve better fairness. However, most debiasing techniques require access to complete training data and the ability to retrain the model from scratch, which may not always be possible. Inference-time safety mechanisms, such as uncertainty quantification techniques and selective classification, are primarily used to enhance the reliability of MLBASED applications. The authors propose applying a similar approach to increase fairness by identifying and debiasing potentially biased predictions at inference time. The main contributions of this work include proposing selective debiasing as an inference-time safety mechanism and suggesting a scoring criterion to select problematic predictions. The proposed approach helps close the performance gap between post-processing methods and at training and pre-processing debiasing techniques in text classification datasets. By identifying and debiasing biased predictions, machine learning models can improve their overall quality and fairness, leading to more reliable and trustworthy applications. Selective debiasing is a novel approach to improve fairness in machine learning models without compromising accuracy. Debiasing techniques can be categorized into three groups: at training, pre-processing, and post-processing methods. Post-processing techniques, such as iterative null-space projection, INLP, and LEAST concept erasure, LEACE, are designed to remove bias from model predictions. The proposed selective debiasing method involves identifying potentially biased instances using a scoring criterion and applying a post-processing debiasing method to these instances. This approach enables flexible adjustment of the accuracy-fairness trade-off. A new bias quantification method is introduced, focusing on group fairness and aiming to eliminate biased predictions while maintaining model accuracy. Unlike traditional uncertainty quantification methods, this approach assesses the fairness of model predictions. A motivational example demonstrates the effectiveness of the fairness oracle over the uncertainty oracle in selective classification. By changing the order of instances being eliminated, fairness can be significantly improved without penalizing accuracy. This highlights the importance of developing a different selection criterion for identifying biased instances. The research suggests that a more balanced approach between fairness and accuracy in machine learning models can be achieved by developing a tailored selection criterion. The proposed selective debiasing method offers a promising solution for improving fairness in machine learning models. By incorporating a bias quantification method and a flexible debiasing approach, this method enables a more nuanced approach to fairness and accuracy. Future work may involve exploring the application of selective debiasing in various domains and developing more sophisticated bias quantification methods. The paper introduces a novel approach to debiasing in machine learning models, focusing on enhancing both fairness and accuracy. It presents the concept of selective debiasing, which targets only the most biased instances for debiasing, rather than applying debiasing to all predictions. This method is particularly beneficial when combined with the LEACE debiasing technique, as it prevents excessive changes in less biased instances, thereby maintaining both accuracy and fairness. The proposed approach utilizes the Kullback-Leibler divergence, KL, to quantify bias in predictions between standard and debiased models. The KL divergence measures the difference in predictions, with higher values indicating more bias. By selectively debiasing instances with high KL divergence, the model can improve fairness without significantly affecting accuracy. Experiments were conducted on two datasets Moji and BIOS2 using BERT and BER tweet models. The results show that the proposed selective debiasing method outperforms baseline methods such as LEACE and INLP in terms of both fairness and accuracy. The paper also presents two aggregated metrics, DTO and FF score, to evaluate overall model performance. In conclusion, the paper presents a novel debiasing technique that improves fairness in machine learning models while maintaining accuracy. The selective debiasing method, along with the KLBASE bias quantification score, offers a promising solution for enhancing model fairness without compromising on predictive performance. Research in fairness-enhancing model techniques introduces a novel selective debiasing method as an inference-time safety mechanism, specifically suitable when model retraining or access to full training data is unfeasible. A complementary approach uses the Kullback-Leibler distance-based bias quantification, demonstrated to surpass uncertainty quantification techniques. Results tabulated in Table 1 exhibit superiority of training and preprocessing debiasing strategies leveraging model retraining with the complete training data, generally attaining improved performance metrics. Selective debiasing outperforms and at times eclipses, when examining dual attributes performance and fairness measures. Studies evidenced from integrating this concept especially heightened output after tests regarding specificity tests scoring specifically and empirical relative evaluations DTO's criteria significantly met between best reached, yielding unforced combined utility estimates leading figures encompass assessment scaling techniques scaling upon employing adjusted precision highlighting margin space leveraging iterative factor variables outcame optimizing scenarios generating several crucial, effective comparative holistic options attains flexibility degrees depending full form effectively depending objective when doing well evaluation integrating UN rank. Reducing difference multi-point training within with limited without optimizing quality having capacity variables utilizing only comparison approaches beyond compare so as basis are considering iterative system pre-optimize working approaches directly developed according adaptation recompute evaluations presented scores consistent use tested optimized case examples maximizing integrating based key selection compared datasets each even effectively the adaptive inference engine component implementing over scenarios obtaining diverse analysis varying combined leading option without large needed leveraging systems selecting potential degrees single compute use output greater real combination that efficiency lead enhancing outcomes shown time scaling well holistic factors present variables clearly developed examples after study referenced then according adjustments only once thus systems proposed showing impact here first selectively making basis techniques depending always balancing adjustment pre-method utilized steps enhanced doing approaches relative beyond adjustments once demonstrated improvement required out clear approaches giving consideration having information overall specific still training now multiple outcomes selecting balance training adapting having achieving varying needs of needed solutions handling existing work addressed towards finality engine applications metrics selectively clearly well including used performing thus large solution was main addressing scenario across comparison scene application diverse without efficiency adjusting certain is utilized these can addressing varied effective model potential evaluated general finding data examined developed examined many the high ability adjustments factor combining studies variable solution has one directly overall beyond which without improvements various especially adjustment selecting those combination is applying improvements components high greater through optimization multi-method finding applying significant making good full showed making found important handling combined being impact proposed leveraging improving made balance utilizing not pre-still leading addressed metric required compared for pre-seen variables evaluations application form but evaluated so performed some important so did techniques applications improvement combined component had from only selection other depending combined are those combination efficiency diverse here models use present fully discussed without comparing best referenced optimizing varying examined seen varied by integrated directly finding selection degree scenario dependent analysis working made especially single specific considering according example developing good data highly case. The study on fairness and debiasing in natural language processing models acknowledges several limitations and ethical considerations. Specifically, the work focuses on group fairness, employing the equal opportunity criterion as the primary metric, consistent with previous studies on the same datasets. A key assumption is access to protected attributes, a common prerequisite in debiasing research, necessary for calculating fairness metrics. The authors emphasize that group fairness and instance-level bias quantification were the primary concerns, driving the ethical considerations. Publicly available datasets and models were used exclusively for their intended purpose, with protected attributes utilized solely for debiasing methods and metric computation. To mitigate potential harm, only attributes that users self-disclosed were employed in the experiments. The study's reliance on self-disclosed attributes ensures that sensitive information is not inadvertently exposed or exploited. However, this approach also introduces limitations, as it may not capture the full scope of biases present in the data. Furthermore, the study's focus on group fairness may overlook individual-level biases, highlighting the need for future research to address these concerns. The use of publicly available datasets and models also raises questions about the generalizability of the findings to real-world scenarios. Additionally, the study's assumptions about access to protected attributes may not hold in all contexts, emphasizing the need for further research to develop debiasing methods that can operate without such assumptions. Overall, the study's limitations and ethical considerations underscore the complexities of addressing fairness and bias in natural language processing models. By acknowledging these challenges, the authors highlight the need for ongoing research to develop more comprehensive and effective debiasing methods. Advances in natural language processing and machine learning have raised concerns about fairness, privacy, and debiasing techniques. A study on fairness without demographics through adversarially reweighted learning has shown promise in eliminating bias in machine learning models without relying on demographic information. This approach involves reweighting the training data to minimize the impact of biased features, resulting in more fair and robust models. Robust and privacy-preserving text representations are also crucial in natural language processing. A previous work proposed a method for achieving this goal by leveraging differential privacy and federated learning. This approach enables the creation of text representations that are both accurate and private, protecting sensitive information from unauthorized access. Pre-trained language models, such as BER-Tweet, have demonstrated remarkable effectiveness in various natural language processing tasks. BER-Tweet is a language model specifically designed for English tweets, and its pre-trained weights can be fine-tuned for downstream tasks, achieving state-of-the-art results. The success of BER-Tweet highlights the importance of domain-specific language models in natural language processing. The paper also explores debiasing techniques for machine learning models, including data preprocessing, regularization, and adversarial training. These techniques aim to mitigate bias in machine learning models, ensuring that they are fair and unbiased. Furthermore, the authors discuss the importance of evaluating machine learning models for fairness and bias, highlighting the need for standardized evaluation metrics and protocols. The author's work has significant implications for the development of fair and private natural language processing systems. By leveraging adversarially reweighted learning, robust and privacy-preserving text representations, and pre-trained language models, researchers can create more accurate and unbiased machine learning models. However, the authors also acknowledge the limitations of their work, including the need for more comprehensive evaluation metrics and the challenges of deploying fair and private models in real-world applications. The authors detailed their training setup and hyperparameters, employing a grid search on the validation set to identify optimal parameters for standard models and debiasing methods. The grid and optimal parameters are presented in tables 2 and 3, respectively. Training was conducted on a cluster with NVIDIA V100 GPUs, with the approximate number of GPU hours spent presented in Table 4. Selective debiasing was evaluated on various percentages of selection, including 5%, 10%, and 15%, with results presented in Tables 6 to 8. The optimal percentage selected on the validation set is presented in Table 9. Notably, the performance of selective debiasing and post-processing debiasing methods trained on a full training set is comparable to the results on only 20% of the data, as shown in Table 5. The authors also compare their proposed selection strategies with other similarity measures, including distance-based measures, with results presented in Tables 10 to 12. The KL score is found to perform comparably or better than the best-performing distance-based measure, and is easier to compute. The synthetic dataset used in the experiments was generated using the make_classification function from scikit-learn, with parameters described in the text. The overall statistics for each dataset are presented in Table 13, and the joint distribution of the target variable and protected attributes is presented in tables 14 and 15. The equal opportunity criterion is defined as a measure of fairness, based on recall values or true positive rates for each class and protected group. The true positive rate is calculated as TP plus Fn, where TP and Fn are true positives and false negatives for a specific group. The TP-R gap is then calculated as the average difference between the true positive rates for each group and the overall true positive rate. Fairness is calculated as 100 times 1 delta, where delta is the TP-R gap. The authors also describe their fairness and uncertainty quantification oracles, used to evaluate the performance of their debiasing methods. The accuracy oracle is built by finding all erroneously classified instances and replacing their predictions with ground truth labels, while the fairness oracle uses protected attributes to detect biased instances. The results of experiments conducted on the MOJI and BIOS-2 datasets using various debiasing methods and selective debiasing are presented. Optimal training hyperparameters for BER-tweet on MOJI and BERT on BIOS-2 were obtained through a grid search, as shown in Table 2. Similarly, optimal debiasing hyperparameters were also obtained through a grid search, presented in Table 3. Computation statistics for the models, including GPU hours spent for training and evaluation, as well as the number of parameters in each model, are detailed in Table 4. The performance of different debiasing methods and selective debiasing on the MOJI and BIOS-2 datasets is compared in Table 5. Evaluation metrics include fairness, accuracy, DTO, downstream task performance, and FF score, which measures both fairness and accuracy. The DADVA method, combining adversarial training with debiasing, achieves the best results in terms of fairness and accuracy on both datasets. INLP, utilizing a fairness-aware loss function, also shows promising results but is outperformed by DADVA. BTEO and BTJLE methods, employing different types of fairness oracles, achieve lower results compared to DADVA and INLP. Selective debiasing, debiasing only a subset of the data, proves effective in enhancing fairness and accuracy. However, the best outcomes are achieved when debiasing is applied to the full training set. Maximal increase in accuracy is also achieved with full set debiasing, and the fairness oracle method, aiming to maximize fairness over accuracy, performs less effectively than DADVA and INLP. These findings suggest that DADVA is an effective method for debiasing and enhancing fairness and accuracy on text classification tasks, and that selective debiasing can be a useful technique for improving fairness and accuracy when debiasing the full training set is not feasible. The mathematical concepts used include grid search, adversarial training, and fairness-aware loss functions. This page's content is connected to previous pages, which detailed the methodology and experimental setup used in the study. The results presented here provide a comprehensive overview of the performance of different debiasing methods and selective debiasing on the MOJI and BIOS-2 datasets. Limitations and future work are not explicitly mentioned, but the study's assumptions involve the use of specific debiasing methods and selective debiasing techniques, and the evaluation metrics used. Future studies could explore other debiasing methods and selective debiasing techniques, and evaluate their performance on other datasets. The results of selective debiasing for LEACE on the last layer and classifier level are presented in tables 6 and 7, respectively, for various percentages of debiasing. The datasets used are MOJI imbalanced, MOJI balanced, BIOS-2 imbalanced, and BIOS-2 balanced. The performance metric employed is the FF score, a fairness-aware metric that measures the trade-off between fairness and accuracy. The tables display the FF score for different debiasing percentages, ranging from 5% to 15%, as well as the optimal percentage for both SR and KL debiasing methods. The results indicate that the optimal percentage of debiasing varies across datasets and debiasing methods. For instance, in the MOJI imbalanced dataset, the optimal percentage for SR debiasing is 10%, while for KL debiasing it is 15%. The FF score values are presented with their corresponding standard deviations, indicating the variability of the results across different runs. Notably, the FF score values are generally higher for the balanced datasets compared to the imbalanced datasets, suggesting that debiasing is more effective in balanced datasets. The fairness metric used as a target metric is calculated by replacing predictions for instances that give the maximal increase in fairness. These predictions are chosen greedily from the erroneous ones. The quality of these oracle strategies is measured using several metrics, including FRAUC, ACAUC, and FF-score AUC, which correspond to the area under the target metric rejection curve. The FF-score AUC metric is used to compare the performance of different debiasing methods and to evaluate the effectiveness of selective debiasing. The area under the curve is calculated on binarized over 100 points target metric values, providing a comprehensive evaluation of the debiasing methods. The results provide insights into the effectiveness of selective debiasing for LEACE on different datasets and debiasing methods. The optimal percentage of debiasing varies across datasets and debiasing methods, and the FF score values indicate the trade-off between fairness and accuracy. The use of fairness as a target metric and the calculation of FF score AUC provide a comprehensive evaluation of the debiasing methods. The following section presents the outcomes of experiments conducted on datasets such as MOJI and BIOS-2, with a focus on evaluating the efficacy of various debiasing methods in mitigating bias in machine learning models. These datasets are characterized by their imbalance and the presence of protected attributes, including race and gender. Tables 812 outline the results of these experiments, comparing the performance of different debiasing methods: selective debiasing, LEACE, LEACE CLS, and INLP on the MOJI and BIOS-2 datasets. The results are reported in terms of the FF score, which measures the fairness of the model. The findings indicate that the optimal selection percentages for the debiasing methods vary across datasets and methods. For instance, the optimal selection percentage for the MOJI imbalanced dataset is 15% for the SR method, while it is 11% for the KL method. Similarly, the optimal selection percentage for the BIOS-2 imbalanced dataset is 9% for the SR method, and 12% for the KL method. The results also demonstrate that the performance of the debiasing methods varies across datasets and methods. For example, the LEACE method performs better on the MOJI imbalanced dataset than on the BIOS-2 imbalanced dataset. Conversely, the INLP method performs better on the BIOS-2 balanced dataset than on the MOJI balanced dataset. Table 13 provides an overview of the dataset statistics, including the number of classes and attributes, the protected attribute, and the train, validation, and test set sizes. The experiments underscore the importance of considering the specific characteristics of the dataset and the debiasing method when evaluating the effectiveness of bias mitigation techniques. The findings also emphasize the need for further research on debiasing methods that can effectively mitigate bias in machine learning models. In terms of equations and algorithms, the paper employs various distance-based scores, including the Euclidean and cosine distances, to measure the similarity between data points. The LEACE and LEACE CLS methods utilize a combination of these distances to debias the data. The INLP method uses a neural network-based approach to debias the data. The study has several limitations, including the use of a limited number of datasets and debiasing methods. Future work could involve evaluating the effectiveness of other debiasing methods and datasets. Additionally, the study assumes that the protected attribute is known, which may not always be the case in real-world applications. Tables 14 and 15 present the joint distributions of demographic attributes and labels in the BIOS-2 and MOJI datasets, respectively. In BIOS-2, the gender profession distribution reveals a significant imbalance, with females predominantly represented in nursing professions and males in surgical professions. This disparity is consistent across all data splits and is accentuated when the data is rebalanced to achieve equal gender representation within each profession. In contrast, the MOJI dataset exhibits an equal distribution of sad and happy emotions across South Asian and African American ethnicities, indicating the absence of significant bias in emotion labels based on ethnicity. These joint distributions are essential for understanding potential biases in the datasets, which can impact model performance, particularly in terms of fairness and accuracy. By examining these tables, researchers can identify areas where data augmentation or rebalancing may be necessary to prevent machine learning models from perpetuating existing societal biases.